Welcome to aminacademy.com. In kinetic theory, let us discuss about pressure of an ideal gas. By the kinetic theory of the gases, assume an ideal gas packed in a cubical container for the computation. The container, one corner serves as the origin, while the edges serve as x, y, and z axis. Let A1 and A2 be the parallel cuboid faces perpendicular to the x-axis. Assume the molecules is traveling with velocities v in a container and the velocity components along three axes where are vx, vy and vz. When this molecule come into contact with the faces, face A1, we believe that collision is an elastic. Now we'll derive the equation. Here velocity components in x, y, z direction is Vx, Vy, Vz. Now, thus the number of molecules with velocities Vx, Vy, Vz hitting the wall in time delta t is half the number of molecules, the number of molecules hitting the wall in delta time t. Hitting in delta t, the time difference is half area Vx. Delta t and number of molecules is n, where n is the number of molecules per unit volume, where n is the delta t into n, where n is number of molecules per unit volume. Now that is equal the total momentum. Total momentum is, so that means that suppose one molecules hit the wall and come back the same position, that is come back to the another wall, opposite to another wall, that is total momentum is 2 times mvx into half n av, half n avx delta t. The force on the wall, therefore force, that is the force on the wall is the rate of momentum transferred, is that is the rate of force on the wall. Force on the wall by the molecule is, that is we can use it the P, which is equal over delta T, which is equal into A also come here, A delta T, which is equal, that is force equal to we have pressure, the same unit having, that is we have N M V x square. This is a one phase. Assume all molecules in a gas do not have the same velocity. There is distribution in velocities. The above equations therefore stands for pressure due to the group of molecules with speed Vx in the x direction, and N stands for the number density of that group of molecules, that is number of molecules per volume, unit volume. The total pressure is obtained by summing all over this contribution due to all groups, that is P can be written further as N M Vx square. This average, that is RMS, root mean square velocity, square of the root mean square velocity, that is Vx square. You can use it bar. This is the average velocities and average velocities of all velocities of the molecules in x direction. Now, similarly, by symmetry, we can say in all direction it is same, that is average velocity Vx in x direction is equal to Vy in y direction, which is equal Vz square. All are same. Now, which is equal, we can say Vx plus both are equal, as well as you can write adding all, that is Vx plus 3 Vx square. Therefore, which is equal Vx square, you can write as 1/3 of the addition of Vx square Vx square Vy square Vz square. So, which is this all Vx square plus Vy square plus Vz square can be written as 1/3 of V square. Therefore, we can write this Vx square equal to total velocity, that is Vx equal to 1/3 V square. Now we can write, therefore pressure on the wall is, we can write as 1/3 into number of molecules N, mass of each molecule, and V square. Average. Here, this is the pressure on the container. P equal 1/3 N into Nm, total number of molecules N. M is the mass of each molecule. V2 square. Sorry, V bar square. Now, some remarks on the derivation in this. The first, though the choose of the container to be a cube, the shape of the vessel really is immaterial. The shape of the container may be other end shapes. For the vessel of arbitrary shape, some other shapes than cube, we can always choose the small infinitesimal planar area and carry through the steps above. Notice that both A, that is area, and delta T do not appear in the final result. There is no, look at in this result, there is no area and volume is not come in this formula. Therefore, it is a material. Means any shape that pressure, average pressure is 1 by 3 n mv square. So we derived an equation of the pressure of ideal gas in a container. If you have done, please subscribe our YouTube channel.